Hello, welcome to DockerCon 2020. Today I'm going to talk about Docker Desktop and WSL2 integration. My name is Simon Ferquel. I'm a developer at Docker, working mainly on Docker Desktop and more particularly on WSL2 integration, obviously. A quick summary about what we'll see today. So we'll begin with an introduction of Docker Desktop architecture for Hyper-V backend, and see how we decided to design the WSL integration. Lastly, we will do a couple of demos, going quite in depth in how Docker Desktop works. So first, Docker Desktop architecture, it's kind of a complex beast. You see, we have a fairly complex architecture because we are running the same application on Mac, Windows. We are doing virtualization, we are doing magic to handle bindments between the host and the VM running Linux. And that means that we have kind of a complex infrastructure to maintain. So when we introduce something like WSL integration, we have to think very carefully about how not to put too much complexity, to add too much complexity to an already quite complex project. So instead of going in depth into every aspect of Docker Desktop architecture, let's focus on the Hyper-V backend. So the Hyper-V backend is what we use to run a Linux distribution that runs the Linux version of the Docker daemon. And so how we do that is that we create an Hyper-V virtual machine in which we run a Linux kit. So Linux kit is a project that allows you to create special purpose distros by assembling a bunch of services that are actually made into container images and having containerd run each of them. So you really need to package only the service that you need, and they will all run in isolation. And one thing that is really funny with Linux Kit is that it's really fast to iterate on building Linux images. So we use that with Docker Desktop, and we assemble our Linux Kit distro out of two ISO files, one which contains the base of the Docker Desktop tools and services, and one that we call the version pack, which contains Docker daemon binaries, as well as Kubernetes. And finally, in order to persist data on disk, we actually create a VHD and we attach that to the distro and mount that in the correct place. Once this Hyper-V VM is started, a little tool that we call VPN-Kit Bridge that allows us to translate Unix sockets that are present within the distro as named pipes on the Windows host. And vice versa, we have a bunch of Windows named pipes that we expose to the Linux Kit distro as Unix socket, and that's this VPN-Kit Bridge utility that does that. From there, when we decided to do the WSL integration, we had a few challenges in mind. First is code sharing. We are a small team, and we want to leverage as much code as possible from our Mac and Hyper-V backends for implementing this WSL backend. And there are a lot of code in there, some APIs for managing the lifecycle of the daemons, things like diagnostic system, upgrade logic, logs, etc., etc. And although Docker Desktop is kind of full-featured, like we have Kubernetes support, we have things like trusted certificate authority, synchronization between the host and the guest. We have a bunch of network settings. We have NAT blocking firewall support, etc., etc. And last but not least, we have, when we first did experiments with WSL2, we found that every WSL2 distro runs in the same network namespace, which is really cool for many scenarios, but it can cause issues for Docker, for the Docker daemon, because Docker does a lot of things related to IP tables, and it does not really support conflicting rules and things like that. And if you imagine running two instances of the Docker daemon in two different distros within your WSL environment, actually things can go very, very wrong, and each daemon will kill its own networking. So we decided to do things a little bit different. So first, LinuxKit distros, like the one we did for Hyper-V, can actually be run as containers, and that's actually a very good way for us to test distros, LinuxKit distros. So what if we could create a simple container within WSL2 with its own mount namespace, its own network namespace, etc., and start a LinuxKit distro in there? And actually, we tried it, and it just works. So if we look back at the Hyper-V backend architecture, what we have for WSL2 is really, really close, actually. So instead of having our own Linux kernel inside our LinuxKit distro, we actually use the Linux kernel that ships with Windows, and we run within the WSL2 utility VM that actually runs every WSL distro. And we have a very small bootstrapping distro, this Docker Desktop distro that you can see when you install Docker Desktop. And this distro is just there to create this namespace to run our LinuxKit container, which is no more a LinuxKit VM, but really a container. And within this LinuxKit container, we have actually the same exact code running as what we have on Hyper-V. So we have the same diagnostic services, use the same lifecycle API, etc., running there. Actually, we share most of the code, not exactly all, but most of the code is shared with Hyper-V in there. And we use the same version pack ISO to get a feeling about how close it is. You can notice a little difference, though. Like on Hyper-V, we did handle persistence using a VHD. We can't attach arbitrary VHDs to WSL2. So what we did is we introduced a data distro, this Docker Desktop data distro that you can see if you look at your list of WSL distros. And we just use this distro to bind mount directories inside our LinuxKit container, so that if for some reason we want to update something from there, we can actually keep your data because it's in a separate WSL distro. And we use the same VPN-Kit bridge, although it runs quite differently. And we did another proxy for handling and interrupt with other WSL distros. And I dig a little bit on that in the demo. So time for the demos. And first, I'd like to focus on the startup sequence. Sorry. So let's go to Visual Studio, and actually we'll run Docker Desktop in debug mode. And this is the code from the front end that actually drives the back end. And so it's this front end code. The first thing that it does is check if WSL is there, and it will call a bunch of backend API. Never mind, and it will actually provision or actually make sure that the necessary WSL distros are provisioned. And so if I go in my terminal here, now if I do a WSL-L, I should see this. So let me enter this Docker Desktop distro for now. So we just deployed it. We didn't run anything at all for now. So if I do a PS3, there we can see that there is nothing running, which is absolutely normal. So let's get back to Visual Studio and go a little further. So the second thing that we do is that we actually start a little process in the Docker Desktop data distro to make sure that WSL doesn't terminate it, and we create a few bind mounts that are accessible from Docker Desktop. So now that Docker Desktop data is started, if I do something like cat proc self mount info, we see that there are a few things like this ISO cache and version pack data that have been mounted in MNT host WSL, blah, blah, blah. And if you look at the VHD, or the virtual disk that is used, like my slash is from SDE, while those one are from SDB, which are actually the device where individual distros are mounted. So yeah, that's something really cool. We can access this Docker Desktop data distro from there. So next, we prepare a bit of configuration files, and we create this config structure, which contain paths to the various ISOs that we need, and a path to the configuration file that will send to the Linux Kit distro. And then once we have prepared our config, we'll actually to run the bootstrapper. And yeah, I think we can just wait for there. So once this is started, if I do a PS3, we can see that there are a few more things that are running. There is this VPN kit bridge stuff, but those expose services from the host to the guest and vice versa. And there is this WSL bootstrap that actually called unshare, which is the Linux utility that we use to create a namespace. And with this, within this new namespace, we have a new init process and containerd running the Linux Kit services. So just to get some insight about what VPN Kit Bridge does. So if I go to run host services, you can see that there is a bunch of Unix sockets there, and that's actually Unix sockets that are proxies to name pipes running on Windows. And it actually does that. VPN Kit Bridge does that both ways. Like all those services running on the guest are actually exposed as name pipe to Windows. So that's the way we handle communication with the Linux environment. So for now, you can see that the guest services doesn't have a docker.sock. That's just because I did not go through the complete startup sequence. So here we go. Linux Kit daemon startup start async. It will actually start a daemon, and now it's there, docker.sock. So we have seen this WSL bootstrap process with the unshare and init thing. So now how did we create this thing? So if you look at tmp docker desktop root, actually there is a root file system prepared there with its own /dev/lib /etc, etc /proc, etc. As the Linux Kit environment runs in its own namespace, we can actually look at what is /proc, for example. It seems empty from there, but we'll see that from within the Linux Kit namespace. Although if I do ifconfig from there, so I'm still in the bootstrap distro, so I'm on the global Linux Kit namespace, network namespace. So you can see that I have this IP address ending with 145. If I go, if I open a new tab with Ubuntu, for example, and but I hit ifconfig, actually I have the same IP address and actually it's the same network interface because both the Docker Desktop distro and Ubuntu distro run in the same namespace. So that's why we create this nested namespace. So let's enter this nested namespace. So ns enter, -a -target. So the init process there is 33. So I'm now in this namespace where actually even my machine name has changed. And if I do ps3 for there, PS3. You can see that within this namespace, we consider ourselves like being in a separate machine, but we are actually running on the same kernel within the same VM as every other distro. So if I do an ifconfig from there, we see that we have a completely different set of network interface, and 0 there doesn't have the same IP, doesn't have even the same MAC address. And actually that's because it's a network interface that we create from a virtual tap adapter, and that's a networking stack that we use for not blocking firewall traversal. So if I do also ls/, you can see that it's actually the same as nested/tmp/docker desktop root that we had before. And from this namespace, it's actually the root of the file system. And something that we do as well is that we actually bind mount between the two things, the guest services, host services, etc. We also bind mount /mnt/c, mnt host c. So it's actually the same 9p share that is used in every WSL2 distro. And so let's go to the Docker Desktop namespace itself. So ls enter -a-t 597, and so Docker runs also inside a nested namespace. But it's not a big deal. But the thing that I'd like to show you is that if I do something like cat/proc self moninfo, and we grep /var/lib, we can see that actually that's something coming from the Docker desktop data. So everything that lives within /var/lib inside our Docker namespace, it's actually something backed by the Docker desktop data distro. So that's how we do persistence. And for sure, if I do something like ls/run/get services, it's there as well. It's mounted there as well. And we also have host c. We also have the 9p mounts there, and actually we have the Docker CLI from there, so I can actually do a Docker info, and it's actually the same daemon. But if I go to my PowerShell there and do Docker info, yeah. So we have started. We have everything exposed to the Windows world, and now, if I go back to my slides, I'd like to do a second demo about Cross-Distro interop. So Cross-Distro interop is the way we actually expose the Docker daemon from your own WSL distro, your own distro. So here I am in Ubuntu, and if I do a Docker info there, actually I'm still running against the same instance of a Docker daemon. So how it works. So first, I'd like to do something like proc self moninfo and give you a little detail about what is inside this mntwsl. So this mntwsl is actually a temp volume that is actually mounted in every WSL2 distro. And it's mounted with shared propagation. So shared propagation means that if I mount something within mntwsl, it's also visible for every other distros. So, like if I go to another distro, like let's go to Fedora. If I do mntwsl test, and I do something like sudo mount --bind, and I mount my root folder into there, my mount directory to empty WSL test. Actually, I can go back to my Ubuntu there and empty WSL test, and I get access to my other distro file system. And so we can actually share some partial visibility across distros using this mnt/WSL. And if I have a look there, we can see that actually Docker Desktop actually share a few things like the guest services and the Docker socket. So one thing that we could do is directly create a symlink from var docker.sock to this guy. But if we did that, we actually would have two problems. First one would be permission, because actually Docker group within the Linux Git environment has not the same, it's not necessarily the same GID as within Ubuntu. And second, every time we do a bind mount, we would actually have a very weird behavior, because the CLI running in Ubuntu doesn't run in the same mount namespace as a Docker daemon. So whenever you try to mount something, the daemon will actually try to mount something from its own mount namespace. So what we do is that we have a little proxy there. And if I do something like docker run, let's mount my home directory in an Alpine container. Oops. Docker run dash. Oh yeah, I missed a -v. Yeah. If I open a new Ubuntu tab there. Oops, not the correct one. And I do some docker ps and docker inspect of this guy. If we look at its bind mounts, we can see that actually the source there has been rewritten to something like run desktop mnt host WSL mounts, etc., etc. And if I do something like cat/proc self mount info, and I get my home Simon directory, we can see that actually it has been bind mounted in this shared thing. And so what we do is that whenever you do a bind mount, we actually translate that under the hood. So we create an intermediate bind mount, we put your source, we mount your source in there, and we rewrite the container config so that it mounts from there. And we do a kind of similar thing for port exposition. So if I do something like docker run /rm -p 80, not 80, but 4242 on 80 nginx. Actually, we do something quite similar. We intercept the creation of the container, and we create some kind of tunneling. So that if I do go there and go to localhost 4242 from my browser, it just works, but it also works from Ubuntu itself. So if I do a curl http localhost 4242, oops, I'm missing a L there, we actually expose that from within WSL2 itself as well. So let me kill this guy and go back there. And actually we do use the same thing, same exposition thing for infrastructure for doing Kubernetes. So for exposing Kubernetes inside your distro. So and that's because we expose the Kubernetes API on the host, but also within the WSL2 environment. And I can go even further and do something like kubectl apply -f this little engine thing, and if I create a load balanced service in Kubernetes, we actually expose that on localhost, both on the host and within WSL. So if I do 2612, we get access to this guy as well. So yeah, it's using the same fundamental there. So let me just stop Kubernetes and we'll go to our last demo, which is about bind-mount performances. So that's one of the goals of our integration with WSL2 is also to improve vastly the performance and mainly the bind-mount performance. And to illustrate that, I have here a little development environment for WordPress. And so what I do there is first I will run that WordPress environment from the Windows CLI. So let me see. Open with code. Yeah. So this directory lives within the Windows file system. And so let's open terminal. And to run this WordPress environment, I just have to do some npm command, npm run of start. And under the hood, what it does is that it uses a compose file which bind mounts the source of WordPress and runs this locally. So with Docker. So if I do a Docker ps there, you can see that this guy running on port 8889. So if I do to localhost 8889, so it has loaded, I will use this developer thing, debugging thing, just to get an idea about time to render a page. So it's between 100 milliseconds and 300 milliseconds mostly. And that's when I bind mount files from Windows. And the reason why it's a bit long is that every single file from the source code, from the WordPress source code, is accessed through a remote file system. And that's not as performant as if we could do that locally. The good news is that, so let me just stop that. The good news is that with WSL2 and the fact that we actually use only bind mounts when mounting things from a WSL environment, the very good news is that if I go to my Ubuntu environment, I actually added the same WordPress application there. And if I bind mount from there, the performance is much better because both Ubuntu and Docker Desktop runs on top of the same kernel. So it has the same cache data structures, the same iNotify eventing system, etc., etc. So we get actually very, very good performance. So npm run and current start. And if I go to the same page, first render is roughly the same, but after that, it's steadily around 20 milliseconds to render the page. And actually, it also handles bind mounts and things like that. And if you use something like your code remote to WSL, you can actually type code.within WSL, and you see that VS Code is actually running as a Windows application, but it says that it's connected to Ubuntu. So I can come there in my IDE and add something in WordPress markup, and yeah, it's live, it's there. Hello, Docker Kern. Okay, so that's all I have for today, and please make sure that you stay little in the chat. I will answer a question there.